Good evening, sir.
हाँ जी, गुड इवनिंग. जस्ट गिव मी 2 minutes. आई एम जस्ट
Sure, sir. Sure.
हाँ जी प्रतिमा, गुड इवनिंग. बताओ कैसे हो? ऑल गुड?
All good, sir. All good.
चलो. और स्लाइड्स विजिबल है, मूव कर रही हैं?
हाँ, एक बार सर मूव करिएगा प्लीज.
ओके ओके, जस्ट अ मिनट.
द फर्स्ट स्लाइड इज विजिबल. या
हाँ
ठीक है.
ओके. और गुंजन ने भी ज्वाइन कर लिया आई गेस. गुंजन, आई कैन सी. हेलो
Hello,
गुंजन.
sir. Good evening, sir.
ठीक है गुंजन, तो वेरी गुड इवनिंग. स्लाइड्स मैं कंट्रोल कर लूंगा. आप नेक्स्ट नेक्स्ट जब भी बोल दोगे, वंस यू फिनिश ऑन योर पार्ट, चलेगा? ठीक है गुंजन, चलेगा?
Yes, sir, चलेगा.
ठीक है ठीक है. तो वेट करते हैं, अभी तो किसने ज्वाइन नहीं किया. अभी सम टाइम वी कैन स्टार्ट. जब भी डॉक्टर प्रतिमा बोलेगी हम स्टार्ट कर लेते हैं.
Yeah. Sir, we usually start around 7:05 or so. When
ओके.
the 20-25 participants, then they keep on joining, sir.
ठीक है चलेगा. ओके.
So good evening, all. Anup sir, I think more than 30 participants have joined.
Okay.
So, welcome all students to session 8 of our OSCE Neonatology and Imaging. Today we have a very important topic on statistics. जितनी बार भी पढ़ लें, I think we need to revise it many times before the exam, and really you need to be conceptually strong in this topic. And today we have Dr. Anup Thakur, senior consultant from Sir Gangaram Hospital, renowned neonatologist, academician, teacher, excellent teacher, and Dr. Kumari Gunjan from Cloud9 Patparganj, and bright alumni from Sir Gangaram Hospital itself. I would request the students to please rename yourselves. Some phone numbers are visible, S1, and so please rename yourself, RV, so that we can actually track your responses. As has been happening, please do type your responses in the chat box. We'll be having the record of the responses, and then we'll be announcing the top scorers also, not only from the weekly assessment but also from this interactive session. Do keep it interactive, and at the end of the session, we'll also welcome some questions on unmute if possible, if time permits. Over to you, Anup sir. Uh,
Yeah. So thank you, Dr. Pratima. And first of all, I'm really grateful to Dr. Pratima, Dr. Swati, and Dr. Sushant for conducting this course of OSCE on behalf of Association of Neonatologists so wonderfully. I think it needs a lot of commitment to sit down for 10 weeks on Sunday and conduct the course, then answer to your queries, and again form a question bank, look at the responses. I'm really thankful from the bottom of my heart to all the team members who are conducting this course, especially, of course, Dr. Pratima and Swati and Sushant. So thank you so much. And today's session is statistics, and we thought that, like this wonderful magician, we should also mix up some ingredient for the students so that they can understand the basic statistics. Now, you have to understand that just like you have a subject of neonatology, pediatrics, in the similar fashion, statistics also is a subject. You can't master it all in one go. You have to bite it crunch by crunch, little by little. And we also tend to learn things as we need some kind of statistical analysis or input for our studies, depending on what is the need of a study, something which might be learning new every day. This is going to continue. You can't master it all at one time. So today I have with me Dr. Kumari Gunjan, who both of us will be taking the questions alternately. So as Dr. Pratima told you, I'm from Gangaram Hospital. Gunjan is from Cloud9, and both of us are neonatologists. And we're going to take this session for you through certain set of questions, and we expect you to answer. Don't worry, we'll pause in between for your responses because we'll be doing some calculations, because when we calculate the things, we understand what is happening. Now, what is the plan for today is to discuss these things in the next 2 hours. In case we are bored, we may take a break somewhere in the midway, so don't worry about that. We're going to discuss distribution of data in one of the questions. All of them are question based. We'll discuss some of the common measurements of central tendency and about a box and whisker plot. We'll discuss Z scores and how we calculate Z score, what are its uses, calculation of confidence interval, of mean difference, of proportions, of odds ratio, relative risk. We'll discuss some of the plots which you commonly see being published, like the forest plot, funnel plot. We'll discuss some of the measures of diagnostic test, like sensitivity, specificity, some calculation, positive predictive value, negative predictive value, likelihood ratio, post-test, pre-test probability. We'll discuss about ROC curve, urine index, type 1, type 2 errors. We'll touch upon some basic elements of sample size calculation and a chart about network meta-analysis. And then at the last, we'll conclude by giving you some examples of statistical test. I think this is the major chunk of statistics that you will be doing day in and day out every day when you read some papers, these are the expressions which are used. And in exams also, the examiners may give you some of the questions based on calculations of these basic statistics. So sometimes they can give you some plots, they can give you some calculation to do. It can be some card-based table viva, or they can give questions of OSCE, which you are supposed to solve in a particular time. So this is usually the pattern in DRNB and DM examinations in OSCE. So I'm going to start it by the question. So Gunjan, should I start the first question?
Yes, sir.
So what we both are going to do, we are going to take alternate OSCEs so that it is not very boring for you. You can have two set of speakers alternately, and that would also keep both the speakers also interested, right? Great. So here goes the first question. And don't worry, we're going to start with something very basic and very simple, and then we'll try to build it up. Okay, so this is the first OSCE which says identify the graph, and you are very fortunate to have a lot of options. Is it a Gaussian distribution, positive skewness, negative skewness, or negative kurtosis? So you can type your responses in the chat box. So I have some responses which say C. C. C, a lot of C's are coming up. C, Shivani is saying she, Gaurav is saying C, Ravneen, Himani, Ekta, Kushal. Okay, so the consensus is right now on C, which is negative skewness. Everyone votes for C. So no more responses, so I'll go ahead. Okay, so there are four terms being used here, and you should be knowing the meaning of each of these terms as you try to understand the question. First is Gaussian distribution. So still someone is typing. C, C, C. Everyone is C so far. Good. So you should know the meaning of these terms. Like I say, Gaussian distribution. So Gaussian distribution is a normal distribution. And in a normal distribution, is a perfectly bell-shaped curve. So it should be perfectly bell-shaped, and the both half of the curve needs to look symmetrical, right? And the mean, median, and the mode, they will be at similar places. The area of such a curve is 1. So let me show you a Gaussian distribution. So the answer is, okay, I'll take the answer also. The answer is B, positive skewness. So all of you who answered C are not correct. It is skewed. Of course, it is skewed because you see it's not a perfect Gaussian distribution. So here you have more mass, more data on the left side, and the tailing is happening to the right side. So this is called the mass. The hump is the mass, and this is the tail of this set of data, right? So this is the tail of the data distribution. Now, so this is not a normal distribution because it is not a perfectly bell-shaped curve, and the mean, median, and mode, they do not coincide, but the mean is more than the median, and median is more than the mode. Okay. Number two, we know that this is a skewed. Skewed means it is a non-normal distribution. Okay. So how to define the skewness, whether it is positive skewed or it is negatively skewed? Okay. So the skewness is defined by the tail of the curve. Remember, by the tail of the curve, not by the hump. So here you see the tail is towards which side, right side or left side? Again, you can type in the chat box. Tail is towards the left side or right side? Right side. Excellent. So tail is towards the right side. So wherever is the tail, that side, we are going to define the skewness. So this data set is skewed towards the right side. That we are clear. So when the data set, the tail is towards the right side, we will say right-sided skewness. When the tail is towards the left side, we will say left-sided skewness. Okay. Right-sided skewness is called positive skewness. The SPSS will give you a positive output for the degree of skewness, +1, +1.5, whatever. Left side skewness is called negative skewness. Okay, so this is the basic about this particular curve. You define it by the tail of the curve. Now, some of the discussions to make it clear, this is the normal curve, normal distribution curve. It's a perfect bell-shaped curve. Both half mirror each other. Most of the distribution, most of the data set is distributed at the center around the mean. The mean, median, mode all will be close to each other. And the total area is said to be 1. Now, in this curve, it is important to understand the concept of standard deviation. So the concept of standard deviation, what is standard deviation? Standard deviation tells you about the dispersion of data around the mean. Okay, how much the data is centered around the mean. Okay, so if you see this is the mean, then one standard deviation on both sides will cover approximately 68.3% of the data set. So 34.15% on each side. Two standard deviation will cover 95.4% of data set, and three standard deviation will cover 99.7% of data set. Let me take an example here. For example, the heart rate, the mean heart rate of a newborn in a population data set is 120. Okay. So when I say 68.3% will have a heart rate between ±1 standard deviation, and if the standard deviation is 20, how do you interpret this data? You can type in the chat box again. Mean heart rate of population is 120. One standard deviation is 20. So ±1 standard deviation, that is 68.3% of population, what will be their heart rate? Okay, I have a response in the chat box. 100 to 140, 140 to 180, 100 to 140, 100 to 140, 100 to 140. Okay, yes. So I said ±1 standard deviation. So if the heart rate is 120 +1 standard deviation, that means +20 goes up to 140. And -1 standard deviation means -20. 120 minus 20 is 100. So 100 to 140, that means 68.3% of the newborn will have heart rate between 100 to 140. Similarly, if I say how, so 95% of the population will have heart rate between what ranges? Same extension now, 95% of the population of newborn. So 80 to 160, right? So two standard deviation, 2SD is 40 here. So 120 plus 40, 120 minus 40. 95% of the newborns will have heart rate between 80 to 160. So that is the beauty about a normal distribution, where you can say the distribution, the dispersion around the mean, if you know what is the standard deviation. Okay. So this was our curve, the right-sided skewed curve or positive skewed curve. Here the tail was towards the right side. The mass of data was towards the left side. And the mean was more than the median, was more than the mode. So mean, median, mode. This is how it will proceed from the tail. In the left-sided data, the tail is towards the left side. This is also called negative skewness. The mass of the data will be towards the right side. And you see mean, median, mode will be distributed like this. Okay. So you define the skewness by the tail of the data set. Remember this. Okay. Next is, I also used a term in the previous question about kurtosis. So we had a term Gaussian distribution, we had a term skewness, and we had a term kurtosis. So kurtosis, it means, the simple terms, it means what is the peakedness, how much is the peakedness of the data set. So if the data is peaking like this, okay, then this is a positive kurtosis. Okay. But if the tails are flat like this and extending, then it is a negative kurtosis. Okay. So positive means most data is centered around the mean. Okay. So when you do your analysis of data in SPSS, it can give you curves like this, and it can also give you values of skewness and kurtosis. So you can understand what is your distribution of data. So skewness, a perfectly normally distributed curve, the value of skewness you will find is 0. If there's a positive skewness, you will get data in plus. So the SPSS software will say plus 1.2, 1.3, plus 2 skewness, plus 3 skewness, and so on. If it is a left-sided skewness, it will give you output in negatives, like -1, -2, and so on. So if your skewness is less than 1 on either sides, we'll accept it to be near normal distribution. And what is the importance of identifying the distribution is that your statistical test and your expression of data will depend on that. So when your data is normally distributed, then what kind of test will you apply? Parametric test or non-parametric test? Parametric test. Excellent. So that's one of the idea to know the distribution, right? If it is not normal, then we apply non-parametric test. And similarly, the expression of data will also change on the basis of that. Okay. So that was about distribution of data. That was about an understanding about standard deviation, dispersion of data around the mean, about skewness, and about kurtosis. Okay. So that ends our first question. I'll quickly go to the second question. So, Gunjan, you can take this.
Yes, sir. Hello, good evening. So, second question is, am I audible?
Yeah, Gunjan, you're audible. I can hear you.
Your department is reviewing the outcomes of very low birth weight infants, that is less than 1500-gram infants, admitted to your NICU over the past year. And you are presented with a chart summarizing the length of stay in days for these infants. So here is this graph. First question is, you have to identify this graph. Second is, what does the value of the box and line inside the box represent? And yes, okay. And last question is, what does the T points beyond this box represent? Good, good. I think it was a very easy question. So most of you have answered it correctly. So this is box and whisker plot. And the box and whisker plot displays the spread of data. And it gives you 5-number summary of a data set. Like this is the minimum. The bottom of the box, this one represents your Q1. That is the first quartile or 25th centile. Then this line inside the box is the second quartile. Second quartile means 50th percentile or the median value. The top of the box, this represents third quartile or 75th centile. And this upper T point is your maximum. So this is the 5-number summary of the data set. And if we take this example, so we can see this Q1, the bottom of the box is corresponding to a value of 25 days. So what do you mean by this? Q1 is 25 days. Can you type for me what does this mean? So Q1 is 25th centile. That means 25% of the babies remained 25 days or less in the NICU. Then top of the box also is 75th centile. And this is corresponding to somewhere to 50 days. So what does this mean? 75th centile corresponding to 50 days means 75% of the infants stayed in the hospital for 50 days or fewer. And now coming to the line inside the box, what was it? This was median or 50th centile. And this is corresponding to somewhere 35 days. And this means 50% of the babies remained in the ICU for 35 days or less, and 50% of the rest remained for 35 days or more. So this was box and whisker plot. And now coming to this box, we know the bottom of the box represents Q1, top of the box represent Q3, that is 25th centile and 75th centile. So difference is 75 minus 25, 50. So this is the middle 50% of the data. Of the whole data set, this is middle 50% of the data set and also represented as interquartile range. What you all have written correctly. So box represents interquartile range and line inside the box represents the second quartile or the median or the 50th centile. Now coming to the third question, what is this T point beyond the box represent? So many of you have answered it correctly, whiskers. So these are the whiskers which represent the data beyond the box. That is beyond the 50% of the middle data. That is your whisker. And this is the upper whisker and this is the lower whisker. So upper whisker represent any data point beyond Q3 to the largest point within 1.5 times of the IQR. So in this case, what it will be? If there is an outlier, so it should be more than Q3 plus 1.5 times IQR. Can you calculate IQR for this question? So I told you Q3 was corresponding to 50 days and Q1 was corresponding to 25 days. So what will be IQR? Q3 minus Q1? Simple, yes, 25. So anything beyond Q3 plus 1.5 into 1QR. So 1.5 into IQR is 37.5, right? Plus 50, that would be 87.5. So anything beyond 87.5 is outlier in this question. And one more thing I would like to emphasize here, this whisker point, this is, I told you this is a 5-number summary of data set. This is minimum, this is maximum. But here I would like to emphasize these are not absolute minimum and maximum. They just stop before an outlier. So for this, it is somewhere at 85, but there are values beyond 87.5 also in this data set, and they are called as outliers and they result in skewness. So I think I'm done with this question. Sir, anything you want to add?
No, that's great. Very nicely explained, Gunjan. So, uh, these whiskers, what are these whiskers for the data, Gunjan? You can just explain to them. This is a range of data, or what are they? So they can be the range of data sometimes. They can be sometimes 95% confidence interval. So you just look at the table notes, what they are, right, Gunjan?
Yes, sir.
Okay, okay, great. This is also for you, Gunjan, I think. Question number
Yes,
3.
sir. Same question, little extension. So same that your department is reviewing the VLBW infants and you have been given this chart of length of stay. Now my question is, the mean length of stay, I'm telling you, the mean length of stay is 42 days and the median is 35 days that we have already seen. What does this signify in terms of skewness? This was actually partly answered in sir's question. It should be easy for you to answer now. And which measure of central tendency is to be used here? Yes. So it is positively skewed because why it is positively skewed? Can somebody answer? Sir, we will stay on that same slide only. Yes, mean is more than median. So it is positively skewed, or we can say it is rightly skewed. Okay. There is one more way to look for skewness in this box and whisker plot. How can we judge just by looking at this box and whisker plot? What is the direction of skewness? Yes, there was one clue that mean is more than median. And another clue, can you take it from a box and whisker plot? So we can see here that the upper whisker is lengthened, or it is like more longer. So whenever the upper whisker is longer, then it is rightly skewed data. Actually, we have to rotate it. Whenever you get an upright box and whisker plot, you can rotate it clockwise. Then you will see that it is upper whisker is on the right side. So if anything is right-handed, it is lengthened, then it is right skewed or positively skewed. And if the lower whisker is lengthened, then it is negatively skewed. So can you give me an example of a rightly skewed data in an ICU setup? One example, though, it is in front of our screen, that length of stay. So we all know that most of our newborns admitted in an ICUs are like moderate to late preterm infants, and they will be staying with us anywhere between 2 days to maybe 2 weeks. But sometimes it will happen that you will have a 24-weeker, 23-weeker, even 23-weeker in your ICU, and they might end up having their ICU stay somewhere between 2.5, 3 months, that is even 90 to 100 days. So this will result in a right skewed data because most of the babies are staying around 2 weeks, and that particular baby is staying for like 90 days. So this directional skewness is on the right side. Again, similar example is like duration of ventilation. In today's era, yes, somebody's answered duration of mechanical ventilation. So in today's era, most of us rely mostly on non-invasive ventilation, and we extubate the babies quite early. And most of the time, we are practicing Lisa or Insure, and sometimes for extremely preterm, we have to keep the baby ventilated for maybe 2 to 3 days. But sometimes we get stuck on the ventilator for maybe 2 to 3 weeks. Then this will result in right skewed data. And then what are the examples of like negatively skewed data or left skewed data in an ICU setup? Can you give me an example? Left skewed data or negatively skewed data example in an ICU setup? You can deduce it from my previous example only. So what I told you, ki most of the gestational age admitted in ICU are moderate or late preterm, but sometimes they are like micro preemies, 23, 24 weeker. This will result in negative skewed data. Most of them are 32, 34 weeker, and one baby you have 24 weeker. That will result in left skewness. And then again, oxygen saturation at discharge. You know ki they will have 96 to 99% at room air, most of the babies you are discharging. But when you are discharging a BPD babies, they might have 90, 91 saturation. So this will result in a negative skewness or left skewness. Then my second answer to second question, most of the you have already answered that yes, median should be the measure of central tendency in this case, because unlike median, they are not influenced by extreme values or outliers. So we will use median in this case. That's it, sir.
Yes, great, Gunjan. I think by now they are clear about the distribution of data, and they are clear about the box and whisker plot, and they're clear about median and quartiles, how they should be calculating, and what is the best way to express it. So now is the question on Z-score, a very simple calculation. Uh, you have a test score of 190, and the mean is 150. The standard deviation is 25, and you assume there's a normal distribution. What should be the Z-score? So Z-score is 0, 1.6, 2.53. You can make a calculation. If you have some idea, if anybody has some idea, you can calculate the Z-score, and then we can take it ahead about the application of Z-score. So Kushal has answered B, Jayati, Govind. So Raja has answered, Tinakaran has answered C. Okay. C, okay, so Prakash has answered it very specifically. He says he makes the calculation and he says 190 minus 150 by 25 equal to 1.6. Okay, Prakash, you made my job very easy. So, Prakash, can you unmute yourself if you don't mind?
Yes, sir.
Yeah, Prakash. Excellent, Prakash. So, carry on. Can you explain to everyone if you don't mind, if you're okay with this, how you made the calculation? Prakash? Okay, so okay, Ashwarya, Shivani, observe minus mean, individual scores minus something, individual score minus mean divided by ST. Okay, so what is the concept of Z score? Is the Z score tells you how many standard deviation the data is, how much away data is from the standard deviation. Okay, so the test score is 190 and mean is 150. Then test score minus mean 190 minus 150 is 40. So it tells you, and then you divide it by 25. So the Z score is 1.6. So it tells you about the data set, how far, yeah, how much it is dispersed from the standard deviation. Okay, dispersion of data from the standard deviation. Okay, that is what a Z score is going to tell you. So this is the calculation of Z scores. Your test data minus the mean divided by standard deviation 1.6. Okay, and it tells you how many standard deviation from the mean your score is. So it's useful in these are the two applications which I have kept here for you. One is for hypothesis testing. So where do you use Z scores in studies? So any example anyone wants to give of Z score being used in studies in hypothesis testing? Or let me make it simple. If you want to compare uh, two groups here. So growth chart, yes. Yeah, growth charts, yes. So very commonly we use in newborns to look at the growth of the baby, and you will see in growth charts also the Z scores are used for BMI, yes. So suppose you are studying a set of population, you are studying some nutritional intervention in a population group A, where you are giving some kind of, say, extra fortification, and group B is your routine fortification, and you want to compare the growth in both the groups. So one of the ways to compare is that you look the, because you understand if you just take weight or some other parameter, they might be influenced by the birth weight. They might be influenced by how the babies will born. So what do? You take an example that you take the birth weight of population A, and then you did the intervention of giving whatever standard population. Okay, and you have taken the weight of the baby at discharge, for example. You want to compare the discharge growth. So then you look at the Z score. What is the fall or gain in the Z score from birth to discharge? Okay. So you have a birth weight and you calculate the Z score. For calculation of Z score of the birth weight now, the mean and standard deviation you will be using from the Fenton's chart. So there is a Fenton calculator available online where if you put your weight of test population weight, it will give you the Z score. So you will have a Z score of the baby at birth. Then similarly, if you put weight of your baby at discharge for the gestation, you will have a Z score. So see what has happened to the Z score, whether it is increased or whether it is decreased. So for example, your Z score was initially 1.5. Now your Z score is say 2.3. So that means it's increased by 0.8. So similarly, you will have this set of data for group A. Similar fall or improvement in Z scores you'll have for group B. You can compare the two data set and compare the Z scores, then which one shows a greater fall or which one shows a greater gain in the Z scores. So that is one use of Z scores in hypothesis testing, and it is a common application in neonatology research studies where Z scores are used. Second is finding outliers. So if your Z score of a data set, if it is lying beyond 3Z scores, then it is an outlier. Okay, 3Z scores is going to be an outlier. There is another application where Z scores are used. Okay, great. So next is your question, Gunjan. You can take this.
Yes, sir. So this I have kept very simple. A trial with new fortified breast milk enhancer is compared against standard fortifier in a very low birth weight infant population. The outcomes are given below. So first question is, what does 95% confidence interval signify? Basically, what does 95% CI mean? Second, mean length of stay is 45 days in standard arm with a CI of 40 to 50. What does this statement mean? I've kept it very simple. You have to just answer what does this statement mean. And is mean difference in daily weight gain? This is the mean difference in daily weight gain. Is this statistically significant or not? So what does 95% confidence interval signify?
Kushal has answered 2SD, so we'll take that discussion also and keep that in mind.
95% of the population is between 42. Yeah, mean length of stay. We can say this with 95% confidence that mean length of stay for this population was 40 to 50 days, right? This was answer to second question. And what is like third one? This mean difference, whether it is significant or not? Not significant for length of stay, significant for weight. Okay. Right. This was this. So Kushal has answered the question which has not been asked even. Good, good. Most of the data set lies between 95 of them. Yes. So, so next slide. So 95% CI represents the range of values within which the true population effect is likely to lie with 95% confidence. That means if we repeat this study many a times, then 95% of those calculated confidence interval would contain the true population value. This is the meaning of 95% CI. And jitna narrow रहता है, the more the narrow is CI, the precision will be more high. And wider CI means low precision. And when this confidence interval includes 1 in for RR or OR, then the result is not statistically significant. And if the CI includes the value of 0 for mean difference, then the result is not statistically significant. Because if RR or OR is 1, that means with or without therapy, there is no difference. So the result will ultimately will not be significant. And again, for mean difference, if the value is 0, that means there is no difference with or without therapy or with or without any intervention. That means if the CI is crossing 0 for mean difference and crossing 1 for RR or OR, then the result will not be statistically significant. So taking this example, sir, question slide. So here mean difference is 3 gram per day. Okay. And we can see what is the 95% CI plus 0.5 to plus 5.5. So does it include 0? No, it is above 0. So this result will be statistically significant if the 95% interval for mean difference, it is not including 0. So this result is statistically significant. Now coming to the length of stay, the mean difference is minus 2.5 days. And what is the 95% CI? Minus 6 to. And here we have to see that this 95% CI is including 0. So this result is not statistically significant. So we saw in this question what is 95% CI. What does a wide CI mean? That means if 95, like in this case, we have plus 0.5 to 5.5. If it was like plus 0.5 to 50, so this CI was very wide. So precision will become low. And if the CI is even more closer, like plus 0.5 to 2 or 2.5, then that would be highly precise. And we also learned that if CI is crossing 0 for mean difference, then result is not statistically significant. And in case of RR or OR, if CI, your 95% CI is crossing 1, then the result is not statistically significant. So this was the summary of this question. Anything else you would like to add, sir?
Yeah, so one more thing I would like to add, there's a confusion, like just someone said that it is same as standard deviation. CI is not same as standard deviation. Okay, first let's understand this. When you are seeing 95% CI in this case is minus 2.5 days and the CIs are minus 6 to plus 1. So there are two groups, standard and new fortifier. So it means in the standard fortification group, if you see the mean is 45 and here the mean is 42.5, the mean difference is 45 minus 42.5. So 2.5 days that we understand, right? And if the CI is from minus 6 to plus 1, it means that the duration of stay in the standard fortifier group can be from minus 6 days. Okay, minus 6 days. So 6 days lesser than to 1 day more. So you see the direction itself is not clear. It could be 6 days less or 1 day more. That is what Dr. Gunjan meant when she said that it is on both sides of 0 or crossing 0. So minus 6 to plus 1. So it could be 6 days less or 1 day more. So therefore, it is not significant. That's number one. Number two, you have to understand that standard deviation and CIs are, what does mean difference signify? Kalyani, can you unmute and ask your question? Don't worry, we are just 40, 50 people. Most of the people are relying on recordings. They're enjoying their Sunday. So you can ask me the question. Kalyani? Dr. Kalyani, you there? Actually, you're on train right now. Okay, fine. See, mean difference means what? You have a mean stay here and you have a mean stay, whatever mean in the two group. Mean difference means difference in the average of the two groups. Difference in the mean of the two groups. That's what mean difference means. Suppose mean height of boys in class 5, section A is 145 centimeters. Mean height of boys in class 5B is 142 centimeter. So the difference between the two is mean difference, 145 minus 142. So you're finding the difference between the two groups. Next question is whether this mean difference is significant or not, for which you find the p-value, and the concept of 95% CI is same as the p-value. If you have the 95% CI, you don't need the p-value, okay? Now, one thing you have to also understand the difference between standard deviation and confidence interval. So standard deviation, you were taking a data set in one sample and you were looking at the dispersion around the mean. Okay, it will tell you dispersion about the mean. Okay. Now, let me presume, let me say, so I'm using the pen for you. Let me say I have 5 samples. There's one sample here, this sample B, sample C, sample D, sample E. There are 5 samples. So I'm going to calculate the mean weight of 20 kids in a area in Delhi. Okay. So there is a mean weight of this sample and the mean weight, there's some mean weight of this sample. Then 20 kids in Kerala. Then I have 20 kids, say, in Gujarat, whose mean I have calculated of weight. 20 kids somewhere in Kolkata, I have calculated the weight. And 20 kids, I have calculated the weight in, let's say, Rajasthan. So the mean, this mean will be different from second mean or not, or third mean or not. Will the means be similar of all this sample? And this all are part of our country, India. Okay, the larger population is India, right? So will this M1 mean of first sample, mean of second sample, mean of third sample, mean of fourth sample, this will be same? They will be different. Good. But these all are samples in the same population, that is our country, right? So for example, the mean of sample 1 is 10 kgs. The mean of sample 2 is 11 kgs. The mean of sample 3 is 12 kgs. Sample 4 has a mean of 9 kg. Sample 8 has a mean of, say, again 10 kg. So all these have different means. Now I want to understand, my problem is not standard deviation. I want to understand what is the mean of the entire population. Because from this sample, I want to know the mean of the entire population of India for the kids who are in 10 years group. So there comes the concept of confidence interval. So if I say the mean of population 1 is 10 kg and the standard and the confidence interval is between 8 to, say, 14, okay, then I know that the mean of this sample is 10, and between 8 to 14, if I take 95 samples, okay, if I take samples of different groups here, then their mean will lie between 8 to 14. So from confidence interval, I'm not looking at dispersion of data set around the mean of one population. Rather, from confidence interval, I'm guessing the spread of the entire population. So while standard deviation looks at one sample, the confidence interval tries to negate the error of different samples. So it looks at the sampling error. It looks at the difference of mean which is happening in different population because of sampling error. Okay. So that is what is the difference between standard deviation and confidence interval. So if I say that the mean is 10 and the CI is from 8 to 11, that means the 95% of these samples, if I take, they will have mean between 8 to 11. That is my level of confidence. I hope the concept is little clear to you that the standard deviation looks at dispersion around the mean, while the CI, the confidence interval, takes care of the sampling error, the difference in mean that is happening because of the different samples. That is what CI takes into picture. So the question is here, I think. This is done by Gunjan. So I've kept two examples for you. So I told you that in confidence and interval, what is important is standard error. And standard error, basically, you have to take into account whenever you are calculating the confidence interval. So 95 percent CI of a mean is mean plus minus 1.96 of standard error. Okay. And standard error is basically standard deviation by root over n. So if you know the mean, so here, for example, the mean is 12 milligram per deciliter. Okay, 12 milligram per deciliter. So there is a drug which is lowering down the serum cholesterol by 12 milligram per deciliter. And you know the standard deviation is 4. And again, you know the total number of subjects is 100. So standard error of mean, you have to calculate the standard error. Standard error is what? It is standard deviation by root over the sample size. Here the standard deviation is 4. Total number of patients are 100. So 4 by root over 100, root 10 is 0.4. So standard error of mean here is 0.4. So if you want to calculate 95% CI, it is mean plus minus 1.96 of standard error. So mean plus 1.96 into 0.4, mean minus 1.96 into 0.4. So mean plus minus 0.78. So that means the drug will lower the serum cholesterol by a mean of 12 milligram per deciliter, and 95% CI will be 12 plus 0.71 and 12 minus 0.71. Okay, that is the way how you calculate 95% CI for mean. For whatever it is, the concept remains the same. 95% CI or proportion also is proportion plus minus 1.96 into standard error of proportion. But the formula for standard error of mean and the standard error of population is different. Standard error of mean had ST root over n, and standard error of population is root over p 100 minus p by n. So the concept is same, 1.96 into standard error, but the formula for standard error of mean, the formula for standard error of proportion, formula for standard error of OR, formula for standard error of RR, all this will remain different. So here, again, I've taken an example. So there's a researcher who tries to perform a study, prevalence of diabetes in 100 subjects, and he found the prevalence to be around 10%. So from here, you can calculate the 95% CI, 10 plus minus 1.96 into standard error of proportion. Standard error proportion is P 100 minus P. So 10, 100 minus P by 100. 100 minus 10 is 90 into 10 divided by 100. So 900 by 100 is 9. Root over 9 is 3. So standard error is 3. So what does it mean here? So when I say the standard error is 3, so what does it mean here? What is your interpretation for this particular question now in relation to prevalence of diabetes? No one is trying to answer. Is it too tough, guys? In 100 subjects, the proportion will be between 7 to 13% if we repeatedly do the study. Okay. So 1.96 into 3. Okay. 1.96 into 3, say, let's say 2 into 3, 6 हो जाता है. So why 7 to 13? 1.96 into proportion, Dr. Prakash. Okay. So 1.96 proportion plus minus 1.96 into standard error. So standard error is 3. Let's say this, let's take this 2 for the sake of calculation. 2 into 3 will be 6. So proportion, whatever proportion is there, 10% plus 6 is 16%, and 10 minus 6 is 4. So 4 to 16. So what I am trying to say now, that the prevalence of diabetes is 10% in this 100 subjects, and the CI is from 4 to 13. So yes, if you repeat the study 100 times, 95% of the times, your proportion is going to lie between 4% to 13% of patients who have diabetes. That is what it means. And broadly, it means that if I take an entire population, say 1,000, 2,000, whatever, and do the study, repeat it in 100 subjects or different samples, different number of samples, each sample could be of different size, then also my proportion will lie between 4 to 13%. Because it's the confidence interval takes care of the error which is happening in your calculation because of different sample sizes. It takes care of the sampling error. That is the broad concept. Okay, got it. Great. So next question is again on OR and RR. Okay. So very simple question now is from the table below, calculate the odds ratio of cancer in non-smokers versus smokers. So you can take 2 minutes, you can calculate. Okay, there are two answers. I will wait. Someone saying A, that is 6. Again, Himani is saying 6. So 6. Shrishti, Ashwarya, what is the answer to this question? Shrishti, you are there? You have disappeared. I'm getting all answers 6 so far. Ashwarya? Ashwarya, you were there, or you also disappeared with Srishti along? You have to participate to make mistakes to understand. Otherwise, it is going to be difficult for you in the exams also. Unless you make mistakes, you will not understand.
Please type your answers, everyone.
Okay, so most of you have answered 666. Monica is answering RR equal to A by A plus B, C by C plus D. Monica, the question is not RR. I want to know the odds ratio, not the relative risk. Okay, few answers for 0.16. Great. So, okay, so what I want to know here is the odds ratio. Okay, I want to know here is the odds ratio of cancer. So my disease in question is cancer, and I want to know the odds ratio in non-smokers versus smokers. Okay, so I have changed the question here. I have not asked you what is smokers versus non-smokers. I'm asking you odds ratio of cancer in non-smokers versus smokers. Okay, and this is a 2 by 2 table in which you are supposed to express your data for calculation of odds ratio, relative risk, sensitivity, specificity, everything. So this is like a kind of gold mine for you, right? By convention, disease is on top and the exposure is on the left side. Okay. Now see here, odds ratio and relative risk, you all know it tells you about the strength of association between two binary variables. So outcome and risk factor. Now, you understand the concept of probability and odds first. So when I say probability, so if I toss a coin and I say that 50% times tail can come and 50% of times head can come, then what is the probability of tails coming? So the probability of tails coming is 50%, you said, right? 50. Then suppose I say that 30% of times, or if I toss a coin 100 times, 30 times head will come and 70 times tail will come. So what is the probability of tails coming now? So if I say 30 times head and 70 times tails, so what is the probability of tails coming? 70, right? So here what we are doing in probability, 70, yeah. In probability, what you're doing, you are taking as numerator the occurrence of events, okay, occurrence of event, and dividing it by total number of the population at risk, okay? Total number of population. So that is probability. Total number, whatever is your event of interest, divide by the total number of population, okay? And probability and risk is same thing, okay? Probability and risk ratio, risk we calculate is same thing, probability and risk. Now in odds, what you do, in odds, you divide the total number of event in which you are interested. So total number of event of interest, say, let's say total number of, here you are tossing a coins. So total number of event of interest is heads coming. You divide it or by total number of events in which you're not interested. Okay. So suppose you're tossing a coin now and 3 times I say 30% probability of heads and 70% probability of tails. So what is the odds of heads coming? %, if I say heads 30 times out of 100 and 70 times I say it's tail, then what is the odds of heads coming if I toss the coin? So here my interest of event is what? Yeah. So here my interest were in heads. So head was 30 times. And an event I'm not interested in was tails. Okay. So 30 by 70, 3 by 7. So grossly speaking, you will basically what you will do, you will subtract the numerator in odds. So probability, which was of heads was 30. Okay. So here it will be like 30 by 100. So that will becomes 0.3 by 1 minus probability. So 1 minus 0.3, so that becomes 0.7. So 0.3 by 0.7. Okay. So in odds, calculation of odds, what you are doing, you are subtracting the probability, the numerator, by 1. Suppose now I am, say, playing Ludo, a dice, and there are numbers 1, 2, 3, 4, 5, 6. There are 6 numbers, right? So 1 can come, 2 can come, 3 can come. So what is the probability of 1 coming if I toss that dice once? If I toss a dice once, yeah. So probability of 1 coming is 1 by 6, right? And what is the odds of 1 coming? One by 5. Yeah, you got it now. Okay. So 1 by 6, you have to subtract 1. So that is the difference between odds and probability. So now you understand. And probability and risk, the terms are interexchangeable. So now coming to the question, this is disease and this is exposure. And I've just written here A, B, C, D, whatever. You don't need to learn the formula. Okay. So when I tell you the odds of having disease amongst exposed. So what is the odds of having disease amongst exposed? So what I do here, I'm interested in exposed. This is what I'm interested. And what is the odds of disease being present amongst exposed? So Kushal is answering A by A plus B. Someone wants to modify it? Kushal, I am asking you odds. And in odds, we discuss that it is the event of interest divided by the event you're not interested in. Okay. So it is not A plus B. A plus B is the total. So A by A plus B becomes probability or the risk. And you have to subtract A from the denominator to calculate the odds, right? So odds becomes A by B. So whatever odds you are supposed to find out, look at the group amongst exposed. What is the odds of disease? So disease is here. So amongst exposed, odds of disease is A by B. Similarly, amongst non-exposed, what is the odds of disease being present? Same way, it will be C by D, right? It will be C by D. What is the risk of disease being present amongst exposed? What is the risk of disease being present amongst exposed? Amongst exposed, risk of disease being present. Okay, A by A plus B. Okay. Similarly, the risk of disease being present amongst non-exposed is C by C plus D. Okay. So you see here, so the odds ratio when I say of the disease being present in exposed versus non-exposed. So odds of disease being present in the exposed is A by B. Odds of disease being present in the non-exposed is C by D. When I ask you the odds ratio, so odds ratio is again a ratio of disease being present in the exposed versus non-exposed, then it becomes A by B divided by C by D because I'm asking you exposed versus non-exposed. So exposed becomes the denominator here. So that becomes A by B divided by C by D. So if I have asked you what is the odds of cancer in exposed versus non-exposed, odds ratio of cancer in exposed versus non-exposed. So first you tell me what is the odds of cancer among smokers, odds of cancer among smokers. Odds of cancer among smokers is 1 by 4. Okay, so 100 by 400, it is 1 by 4. Great, good, Govind. Now you tell me what is the odds of cancer amongst non-smokers. So non-smokers is 20 by 480. So that becomes 1 by 24. Excellent. So forget about A, B, C, D. Don't go by A, B, C, D. You go by the language. Like I say, odds of cancer amongst smokers. So I will look the smokers row and then find out cancer. Then I say you odds of cancer amongst non-exposed or non-smokers. So non-smokers is my interest. So I look at the non-smokers and look at the disease. Okay. So 100 by 400 is the odds of cancer among smokers. 20 by 480 is the odds of cancer amongst non-smokers. Now I can ask you the questions either ways. I can ask you, tell me the odds ratio of cancer among smokers to non-smokers. In that case, your calculation becomes 1 by 4 divided by 20 by 480. Because I am asking you odds of cancer among smokers versus non-smokers. Now, if I ask you the question in the reverse way, tell me the odds ratio. Yeah, that is 6, Nikha, you're right. Now, what I asked you in the question was, tell me the odds of cancer in non-smokers to smokers. Odds ratio of cancer in non-smokers to smokers. So now your calculation becomes what? So odds of cancer in non-smokers is what? 20 by 480. Okay. And odds of cancer in smoker is 100 by 480. So your answer will be 20 by 480 divided by 100 by 400, and that will give you 0.16. Okay. So the question may be asked in either ways. You should be ready to understand. And if you do this A, B, C, D, then you are going to mess up in the examination. Okay. You just try to understand the concept, make a 2 by 2 table, see what the question is being asked, odds of cancer in smokers. Then I look at the smokers, I look at cancer and calculate the odds. Odds of cancer in non-smokers, then I look at the non-smokers row and look at the cancer. So 100 by 400, 20 by 40. So that's how you calculate the odds ratio. For risk, it will be 100 by 500 and it will be 20 by 500. So risk of cancer in smokers will be 100 by 500. Risk of cancer in non-smokers will be 20 by 500. Risk of cancer in smokers versus non-smokers will be 100 by 500 divided by your 20 by 500. So that's how you're going to calculate the risk ratio. Okay. So that is what we calculated right now. Odds of cancer in smokers 100 by 400, non-smokers 20 by 480. Odds of having a lung cancer in smokers to non-smokers 1 by 4 divided by 1 by 24, that is 6. And the interpretation here is if the odds ratio is more than 1. Remember, it's a ratio. In mean difference, the concept was that CI should not be crossing 0. In ratios, the line of equivalence, it is 1. So if the ratio is more than 1, it means increased risk. Okay, so here see the ratio is 6. It means increased risk. And the CIs, they should not be including 1. That means both the lower limit and the upper limit of the CI should be more than 1 so that the odds ratio is becomes significant. So odds ratio is 1, CI is between 1.5 to 3.5. That means significant. Odds ratio is 1 or 1.5, but the CI is between 0.5 to 3.5. It is not significant. So that also you have to keep in mind. And this was the question I asked you, non-smoker to smoker, and we just learned how to calculate it. So here the odds ratio of cancer in non-smoker to smoker was 1 by 24 divided by 1 by 4, which was 0.16. That means decreased risk. Okay, it is less than 1. Odds ratio means decreased risk. That means there is 84% chance reduced risk of lung cancer in non-smokers as compared to smokers. This is how you will calculate odds ratio and relative risk. Okay. So any questions here? Because this is a very important concept and you all should be not missing on this, at least as EM or fellowship students. No questions, then we can proceed. Okay, great. This we have already discussed about the inclusion or exclusion of one, right? Okay, Kunjan, you can take this question number 7.
A recent meta-analysis evaluating the efficacy of a new biological therapy compared to a placebo for preventing severe exacerbation in children with uncontrolled severe asthma. Has been shown by this forest plot and this question. So, what does the square represent here? And what does the figure tell you about the effectiveness of the new biological therapy? And what does this line at 1 signifies? Somebody has answered sample size. Square represents sample size. Any more answers? You can post it in your chat box. Effect size of individual study. Square is weight of each study. The new biological therapy is favoring line. Line 1 is line of no effect, right? So the square here represents point estimate or RR of each study, individual study, and the size of the square that will represent the weightage of the study. What was the sample size included in that study? So here we can see the larger, actually more or less study A and study C, they look alike, and the smallest square is like study E. So the most of the weightage the study will be for study A and study C. And this horizontal line between this square, that represents 95% CI of that individual study. Now coming to the second question, what does the figure tell you about the effectiveness? So somebody has answered yes, this biological therapy in question is effective intervention. How can you tell this? So diamond at the bottom, this is the represent the pooled effect of all the 5 studies above. And what we can see here is center of the diamond is corresponding to somewhere 0.4. That means the babies who are in intervention arm, they have 40% less acute exacerbation of severe asthma as compared to the control group or placebo group. That means a risk reduction of around 60%. Also, this width of this diamond, this horizontal width of the diamond, this is not crossing this vertical line. So this means that whatever result you have got, that is statistically significant. In this case, that this biological therapy in question is effective therapy for control of acute exacerbation of severe asthma. And somebody has answered line at 1 signifies line of no effect. Yes, it has already been written in this forest plot. This is line of no effect. Because if RR is 1, that means therapy or no therapy, the risk will be same. So this is no the line. This is line of equality or null effect or line of no effect. So this was the forest plot for all of us. So we will summarize this. On the left, we have all the studies, individual studies, study A, B, C, D, E, and even the years are mentioned here when they have been conducted. Then all this square represents the point estimate of individual study. As we have discussed that the greater the size of the square, more is the weightage of the study in that meta-analysis. And this horizontal line between the square, this represent the 95% here. So all of these studies, we can see that they are not crossing this line of no effect. So individual study in itself, they are statistically significant. The result they are showing that biological therapy in question is effective therapy. And then bottom, we can see the diamond. This is the pooled effect of all the study. Center of the diamond is what represent the RR here, and the horizontal width of the diamond. If it is crossing the line, the result is not statistically significant. If it is not crossing the line, wherever it is, that is favoring that agent. If it was on the right side, then it was favoring the placebo. If it is on the left side, then it is favoring the biological agent. And we have already discussed this line of no effect. So there is one more thing, heterogeneity. So I square represents the heterogeneity in the meta-analysis. 25% is fair enough. It's a good thing. What do you mean by heterogeneity? That what was your sample size? If there was difference in the type of population you have taken and severity of asthma you have included in your study, different kind of different individual study, was the population different or heterogeneous? If I square is more than 50%, then heterogeneity is fair enough. If it is more than 75%, heterogeneity is high. And if it is 25 to 50%, it is acceptable. So I think that's it, sir. We can show the answers. We can move the slides, sir. I think we have already discussed all these things. So next question is about this plot. A meta-analysis that evaluates the efficacy of a specific multi-strain probiotic in preventing antibiotic-associated dysbiosis and restoring gut microbial balance in pediatric patients. So what is this plot in the slide? And what is your interpretation of plot in regards to pooled analysis? So somebody has answered funnel plot, publication bias because asymmetry, funnel plot, yes. So yes, it's a funnel plot, which is a scatter plot, and it helps us in detecting publication bias in a meta-analysis. So we will briefly decode this plot for you. So this x-axis represents the effect size or effect estimate. And here the left side is favoring the probiotic and the right side is favoring the control. Now on the y-axis, we have standard error. Here, top part of the study, top part of the plot, this will contain most of the larger studies with a low standard error. We can see here y-axis higher is y-axis value is low standard error. So top part of the funnel plot will be containing larger studies with a low standard error, and the bottom part of the funnel plot will be containing smaller studies with higher standard error. Now coming to this vertical line. This vertical line represents the pooled effect of the study. Here we can see this is corresponding to log minus 0.4. Minus 0.4, and we have seen what is in the left side favoring probiotic. So this study is favoring that probiotic helps in preventing antibiotic associated dysbiosis. But we have to take this result with a pinch of salt. Why? Because what we can see, if there is no publication bias, studies should fall symmetrically in the funnel plot. Here we can see larger studies are on both sides of the plot, right as well as left. But bottom part, where smaller studies are included, they are only present on the left side, not on the right side. Right bottom part is the missing. So there is definitely publication bias. What we can see is smaller studies will overestimate the effect. So this is overestimating the result in favor of probiotics. Also, we do not have any kind of smaller studies in this which represents negative study or neutral results. They are not present on the right side. That's why this study is highly, this has a publication bias that smaller studies and studies with negative results has not been published. And this shows that uh, uh, although this study is favoring the probiotic, but there is a huge publication bias here, and we have to repeat studies in different population with more smaller studies favoring control or placebo. So this was it. So this is a funnel plot, and this we have already studies that we have already discussed that top part is containing the larger studies and the bottom part is containing the smaller studies. This one I have missed. This dashed triangular line, they represent the 95% CI. And of course, this plot is asymmetric because right bottom part is missing. And there are many studies, smaller studies favoring probiotic, but no such studies on the right side, which shows no benefit or harm on the right side. So that was funnel plot.
Okay, Gunjan, what we'll do, we'll take a 5 minutes break. Let them have some breathing. Otherwise, they must be already saturated. So much difficult calculations and too much. So we'll take a 5 minutes break and come back in 5 minutes. So just go have a glass of water, stretch out, and come back. Pratima, is it okay for 5 minutes break? Okay, let's take a 5 minutes break. We'll come back. Okay, so those who are there, they can start doing the calculations. So the question is, let us presume that out of 200 children in the study, 60 have positive CRP, and of those 60, 45 have blood culture positive, and 50 patients uh, in total have a positive blood culture. So what is the sensitivity, specificity you can calculate? So anyone is able to answer the question or do the calculation, you can type your response in the chat box. Okay, I can see some responses. I'll just maybe wait for 1 or 2 minutes, then we'll go ahead. Okay, A, great. That means most of you know the concept. So sounds good. Any more responses? Great. So Gunjan, you are there. Should we go ahead now?
So
Okay, great. So most of you know this concept. The idea is to reinforce this. First of all, you whenever you calculate these kind of parameters for diagnostic tests like sensitivity, specificity, positive predictive value, negative predictive value, always make a 2 by 2 table like this. Okay. So the question was there were 200 kids, a total of 200 kids, and 60 had positive CRP. So by convention, disease is being written on top, sepsis positive and sepsis negative. And the test is on the left side, CRP positive and CRP negative. So 60 had a positive CRP, 60 had positive CRP, of which 45 had blood culture positive sepsis. So of which 45 had blood culture positive sepsis. So this becomes 60 minus 45 becomes 15. Then another information which we have is that 50 patients have a blood culture positivity. So 50 patients have blood culture positive. So 45 have positive CRP, rest 5 have a negative CRP, right? And now from 200, if you subtract all this thing, you'll get here 135. And this is how you get the 2 by 2 table. Now for calculation of sensitivity and specificity, I just want you to remember one statement for each one of them. So sensitivity is probability of test being positive amongst disease. Okay. Probability of test being positive amongst disease, and specificity is probability of a test being negative amongst non-disease. This is the concept which you have to remember. Don't try to remember by TP, by FN, by TP, by FP on all those kind of formulas. That will confuse you in the examination. Just remember probability of test being positive amongst disease or disease positive, and out of that, how many are test positive. So let's look at your 2 by 2 table. And if you look at your 2 by 2 table and see, I want to find out the probability of test being positive amongst disease. So my working column or working row is amongst disease, right? So if I see here, this is the disease, sepsis positive is the disease. So this is the column where I'm supposed to work because I am interested amongst disease. So amongst disease, what is the probability of test being positive? So test positive is CRP positive, test negative is CRP negative. So test positive, probability of test being positive is 45. So amongst disease, my denominator is amongst disease. So disease total is 50. And what is the probability of test being positive? The probability is 45. So your sensitivity is 45 divided by 50, which is 90%. So as simple as that. So you have to just remember what is the concept of, or what is the definition. That will lead you to the calculation very easily. Okay. Now the next question is what? What is the specificity? Okay, what is the specificity? So in the specificity, what is the denominator? Denominator is non-disease. So my working column here is non-disease. So here my disease in question is sepsis. So I'm going to work in the column of non-disease, which is sepsis negative. So this is my working column and this is my denominator, right? Amongst non-disease. Next is amongst non-diseased, what is the probability of test being negative? So I have to find out test negative. So what is test negative here? Test negative is CRP negative, which is 135. So amongst non-disease, that is 150, test negative is 135. So my specificity is 135 by 150, which is again 90%. So if you remember the concepts right like this, and if you remember what is your working column, it makes the calculation very easy. Okay. So sensitivity, higher the sensitivity, lesser is the false positive rate. Okay. So false negative rate. Okay. So as you see in sensitivity, you have the false true positive divided by the false negative. False negative you have below. So lesser the false negative rate, higher is the sensitivity. Okay. And in specificity, you have true negative on top and you have false positive on bottom. So lesser the false positive rate, higher is the specificity. Okay. A sensitive test, if it is negative, it will rule out a disease. So you remember by the mnemonic SNOUT. A sensitive test, when it is negative, it rules out a disease. A specific test, if it is positive, it rules in a disease. Okay. So that is the broad concept of sensitivity and specificity used to look at a diagnostic test to compare it against a gold standard. Okay. Next, Gunjan, this is yours. You take this.
Yes. So a new biomarker, procalcitonin, is being evaluated for diagnosing neonatal sepsis in an ICU. Here is the 2x2 table, and the study results are shown below in this. And first question is calculate the positive predictive value and negative predictive value, and what happens to positive predictive value if prevalence decreases. So first, you have to see this 2x2 table. You should know what does this literal meaning of positive predictive value means, literal meaning of negative predictive value means, and then we can calculate it easily. So I'm waiting for the answers. 66 and 93, okay. Anybody else would like to answer? PPV decreases. Okay. So, literal meaning of positive predictive value, like sir said, for sensitivity, it was test positive among the diseased. Here it is the probability of being diseased among all the test positive. The probability of being diseased among all the test positive. So denominator will be all test positive. So what are the test positive? Either it is true positive or false positive. So here this is sepsis present and test positive. Both are present, that is true positive. So 40 will be your true positive. And what will be the false positive? Here we can see test is positive, but sepsis is absent. That is 20. So 40 plus 20 in the denominator. And out of this, all the test positive, how many of them are actually diseased? That is 40. So 40 divided by 40 plus 20. Are we clear? 40 divided by 40 plus 20, 40 by 60. That will come around, I think, 66.7%. So whoever have answered, they have answered it correctly. So if positive predictive value is 66.7%, that means that if the test is positive, there is a chance of 66.7% that the person is diseased. Now coming to the negative predictive value. This means what is the probability of not having the disease or being non-diseased among all the test negative. So denominator mein all test negative will be there, whether it is true negative or false negative. All the test negative results will be in the denominator. So let us deduce from here. So here test is negative and sepsis is present. So this is your false negative. And test is negative and sepsis is absent. This is your true negative. So denominator will be 130 plus 10, that is 140. And numerator, what we have said, all the non-diseased among all the test negative. So this is the test negative column, and we can see sepsis is absent among 130 patient out of 140. So 130 divided by 140, that is coming around, I think, 92.7% or 93%. So in this case, if the test is negative, there is 93% chance that the person in question will be non-diseased or free of disease. That means negative predictive value. So here we have to remember that what is the literal meaning of PPV? That is probability of being diseased among all the test positive. And what is NPV? Probability of not having the disease among all the test negative. Clear? So what happens to PPV if prevalence decreases? Again, somebody has answered in the chat box, it decreases. Yes, it decreases. So let me explain. So whenever a prevalence of a disease for a particular population decreases, what does that mean? Next slide. What does that mean? If the prevalence is decreasing, so whoever is testing positive, chance is that that test can be false positive because overall prevalence is decreasing. So false positive rate will increase. And what we have seen earlier, that your positive predictive value was inversely proportional to your false positive rate. So previous slide. One more. Yes. So if the prevalence is decreasing, what will happen? That whoever is testing positive, chances, because overall disease is low in that population. So whatever positive test is, that can be more of false positive. So we can see PPV is inversely proportional to false positive. So what will happen is, if false positive is increasing, PPV will decrease. And in terms of prevalence, if prevalence is decreasing, PPV will also decrease. And what will happen to negative predictive value? If prevalence is decreasing, what will happen to negative predictive value? Yes, because overall, whoever is testing negative, there is more and more chances that they are actually truly negative. So negative predictive value, we can see this is directly proportional to true negative rate. So it will increase. So this is the difference between sensitivity. One of the differences between sensitivity and your predictive values, that these predictive values depend on prevalence. And if the prevalence is decreasing or increasing, they might change, but sensitivity and specificity, they won't change. So next slide, I think that's it. If you want to add something, sir.
No, I think you explained it, Gunjan, already. So if they remember the simple concept that sensitivity is probability of test being positive amongst disease, and specificity is the probability of test being negative amongst non-disease. Positive predictive value is basically disease positive amongst test positive, and negative predictive value is disease negative amongst test negative. So take the denominator first, and then you put the numerator. From 2 by 2 table, it becomes very easy. Okay, now next question. We are going maybe we have just 15 minutes left, and we are going little higher on the difficulty level. So next, the same 2 by 2 table for you. You have to calculate now the positive likelihood ratio and the negative likelihood ratio. So maybe I'll wait for 1 or 2 minutes, then
Right on
I'll
that.
start answering the question. Yeah. Okay. So Kushal has written B. Anyone else wants to answer this question? Positive likelihood ratio and negative likelihood ratio in terms of CRP for sepsis. So we want Prakash, you're going to try this. Aishwarya, you have to try this. Shrishti is still there. I thought she might have left the class. Sogi Yogi. Shrishti, you can try this now. So Aishwarya is writing B. Monica is writing B. Kushal is writing B. Okay, great. So we'll discuss this. See, basically, again, you have to remember the one line definition. That's what we are trying to tell you. One line you have to remember about each of this so that you don't confuse. Now, why we need to do positive likelihood ratio and negative likelihood ratio is that right now you just saw that positive predictive value and negative predictive value are influenced by prevalence. So PLR and NLR, positive likelihood ratio and negative likelihood ratio, are not influenced by prevalence. That is one advantage. Second advantage is that if you talk about PLR and NLR, they take into account both disease positive and disease negative. So, for example, you were taking sensitivity, you were taking into account only disease positive. So, test positive amongst disease positive. Or you were taking into account specificity, you were taking into account test negative amongst disease negative. Now, positive likelihood ratio and negative likelihood ratio takes the probability of test being positive or negative both amongst diseased and non-diseased. So that is the advantage, and therefore they are more robust statistical tests. So if that is the answer, now I just want you to remember one line here that a positive likelihood ratio, PLR positive, when I say, then it is probability of a positive test because we are talking about positive PLR, probability of positive test in disease subjects compared to probability of positive test amongst non-disease subjects. So test positive amongst disease divide by test positive amongst non-disease. So PLR, so test positive, and I told you it takes into account both diseased and non-disease. So test positive amongst disease divide by test positive amongst non-disease. That is your positive likelihood ratio. Similarly, negative likelihood ratio is test negative, right? So because it is negative likelihood ratio, so test negative amongst disease versus test negative amongst non-disease. So taking care of both disease and non-disease. So if you remember this much, then the working becomes very easy. So positive likelihood ratio, test positive amongst disease versus test positive amongst non-disease. Negative likelihood ratio, test negative amongst disease versus test negative amongst non-disease. So that much first you have to remember. So you see here, this is your 2 by 2 table. So positive likelihood ratio, I told you, first you have to see what? You have to look at the, let me get the pen for you and let me minimize this. Yeah. So first you have to see for positive likelihood ratio amongst disease, test positive. So amongst disease, my working column is this, amongst diseased. Okay, this is my working column. I'll just get my pen. Yeah. So amongst disease, this is where I'm supposed to work. So amongst disease, test positive. So amongst disease means out of 50, test positive is 45. Okay. So that is my first calculation. Amongst disease, test positive is 45 by 50. Then it has to be divided by test positive amongst non-diseased. So I go to my non-diseased column, which is here, non-diseased. So this is 150. And I have to see how many are test positive. So test positive here are 15. So 15 divided by 150. So I then divide this by this. So test positive amongst disease divided by test positive amongst non-diseased. So this is here 45 by 50 divided by 15 by 150. And that gives you a positive likelihood ratio of 9. Okay. So we are just going by the definition, or we are just going by the what it means by the calculation, right? Now let's talk about the negative likelihood ratio. So I told you what is negative likelihood ratio. Negative likelihood ratio is basically what? Test negative amongst disease. So again, I go to the disease column, okay, and I see test negative. So this is my interest. So test negative 5 amongst disease. So amongst disease, out of 50, how many are test negative? 5 by 50. Then next is what? It has to be divided by test negative amongst non-disease. So amongst non-disease, I have to find out. Amongst non-disease is this one is my working column. Amongst non-diseased, how many of them are test negative? So 135 out of 150. So 135 out of 150. So test negative amongst disease divided by test negative amongst non-disease. This is my negative likelihood ratio. Okay. So if you remember this much, the concept, then the calculation becomes very easy of PLR and NLR. Okay. Now, what is the use of this? Use of this is if you get a PLR of more than 10, positive likelihood ratio of more than 10, and negative of likelihood ratio of less than 0.1, then the test is very good in that sense that it is a very good PLR or a negative likelihood ratio. Okay. So any questions in PLR, NLR, or we can proceed, Gunjan? Any
Yes.
questions you can type in the chat box, we'll take it.
So moving to the next question. A researcher is evaluating a new biomarker, that is serum procalcitonin, for diagnosing neonatal sepsis. And the diagnostic accuracy of the biomarker was assessed using a ROC curve, receiver operating characteristic curve. You are shown the ROC curve comparing different cutoff values of procalcitonin for diagnosing neonatal sepsis. So next slide, sir. So this is the different cutoff value and sensitivity and specificity at that particular cutoff value. And this one is your ROC curve. So first question is define ROC curve. Simple. Second one is explain what area under the curve represents. And here AUC we can see in the previous slide was 0.87. What does that mean? And what is Uden's index? And what is the optimal cutoff value for diagnosing neonatal sepsis in this case? Graphical presentation of validity of a test. What is the x-axis and y-axis for ROC curve? Yes. We are plotting sensitivity against false positive rate or 1 minus specificity. And yes, this is a graphical representation too. Used to best cutoff point, okay. And what does the area under the curve represents? Overall quality and accuracy of the test. And 0.87 value, UC is 0.87 here. What does that mean? Overall performance of the test. Is very good. It tests to discriminate between diseased and non-diseased subjects, and 0.87 is very good. And what is the literal meaning of AUC of 0.87? Can you elaborate? What is the literal meaning of AUC of 0.87? So if we, okay, sir, move the slide. So a receiver operating characteristic curve, like you said, is a graphical presentation used to evaluate the diagnostic performance of a test. And we are plotting sensitivity against false positive rate at different cutoff values. This was important. And AUC, as you said, this is the overall ability of the test to discriminate between disease and non-disease individual. And AUC 0.87, area under the curve of 0.87 is excellent diagnostic performance. By that, we mean that if we randomly pick a diseased and non-diseased individual, then there is 87% chance that the test will assign a higher value for the diseased person. And um, sir, can we go back to the ROC curve slide? Yes. If the cutoff, the cutoff which is closest to the top left corner, where sensitivity as well as specificity is the highest, that is your optimal cutoff. This is one way to find the optimal cutoff. And another way we can calculate the Udens index. So Udens index is a statistic used to determine the optimal cutoff value for a diagnostic test on an ROC curve. And this test has the best, it identifies the point where there is the best balance between sensitivity and specificity. So formula by formula, if we go, Udens index is sensitivity plus specificity minus 1, and it is denoted as J. Now coming to this particular question, so at cutoff of 0.5, we can see sensitivity is 95%, which is excellent, but specificity is poor, that is 50%. And calculating the Udens index, 0.95 plus zero point 0.5 minus 1, that is 0.45. Now moving to the next cutoff, that is 1. Here sensitivity is again good, 85%. And specificity is also somewhat balanced, 75%. And here the Udens index is 0.6. Moving to the next value, 2. Cutoff value of 2 nanogram per ml. Sensitivity is further has fallen down to 70%, but specificity is high here, 90%. And again, the Udens index is 0.6. So in this particular question, we know that cutoff with the highest J value is considered the best diagnostic threshold, but we have two Udens index, which are two cutoff value where the Udens index is same, that is 0.6. Then how to decide which cutoff is the optimal cutoff here? So here at 1, cutoff value of 1 nanogram per ml, we can see there is a better balance between sensitivity and specificity. Sensitivity is also good, specificity is also acceptable. And at 2, somewhat sensitivity is lower down. Also, in case, because in this particular question, we are talking about neonatal sepsis, and we do not really want to miss out on sepsis. So wherever, whichever cutoff value has a higher sensitivity will be the optimal cutoff value. So here we will take 1 as the optimal cutoff value in this case. Because we have already discussed all these things.
Okay. Okay, Gunjan. That's fine. I think just 2, 3 slides maybe, and we finish up. It's already 9. We have exceeded the time. Okay, so this is another example for you how to calculate a post-test probability. So this is then basically an application of likelihood ratio which we calculated, how it is applied in clinical sense that you can understand. So the pretest probability of sepsis based on clinical signs. So you just saw a newborn baby and you think newborn has some signs of sepsis, maybe some apnea, some feed intolerance. And based on your experience, you think that the probability of this baby having sepsis is 90%. And you sent the blood test and you got a CRP. And from the calculation, the likelihood ratio of positive CRP from a previous study is said to be 9. And likelihood ratio of a negative CRP is said to be 0.11. So with a pretest probability of 30% of sepsis, and with this information, with a PLR of 9 and NLR of 0.11, how do you calculate the post-test probability? If you know the question, how to solve it, that would be great. If you don't know, then I will quickly proceed. So I'm having a few answers in the chat box. ability of test, 79% has been answered by Kushal. Okay. Prakash says it is difficult. Okay. Aishwarya, can you calculate? Shristi, Sujoy, Tanisha, can you calculate? Anyone is doing the calculation or should I go ahead? Okay, so how this calculation works? See, basically you have a pre-test probability. So you examine the baby and you think the probability of this baby having sepsis based on your clinical signs is approximately 30%. And now you send a CRP test, and from studies you have the LR of positive CRP, that is PLR is 9 and negative CRP is 0.9. What will happen to your prediction or probability depending on whether the test is positive or negative? That is what we're going to calculate. So here, basically, you're going to use the likelihood ratio, whether you want to use PLR or NLR, depending on whatever you want to use. So you can calculate the post-test odds from likelihood ratio. Here, what you have been given is you have given a probability. You have given the pre-test probability. So first you have to convert pre-test probability into pre-test odds. Okay. So first you convert pre-test probability into pre-test odds. Then you can multiply it by likelihood ratio. The pre-test odds you can multiply by likelihood ratio. That will give you the post-test odds. And then from the post-test odds, the next step is to calculate post-test probability. So for this, your concept of odds and probability should be clear. So pre-test odds. So remember, the odds is P by 1 minus P, probability by 1 minus P. Okay. So pre-test odds become what? Your probability is 30%. Okay. So 30 by 1 minus 30. So here we'll take 100 because you're taking 30%. So 30 by 100 minus 30, which becomes 30 by 70 or 3 by 7. So from a pre-test probability of 30%, your pre-test odds is 3 by 7. This we also took many examples of coin. Okay. So pre-test probability was 30%. The pre-test odds becomes 30 by 70, 3 by 7. Now post-test odds you can calculate by multiplying the pre-test odds with likelihood ratio. So here I am taking as an example of positive likelihood ratio. For example, your test has come positive. Your CRP is positive in the baby. So what you do, you will multiply the pre-test odds into likelihood ratio. So pre-test odds is 3 by 7 into your positive likelihood ratio was 9. So I multiply 3 by 7 into 9 and my post-test odds I get is 3.85. So from pre-test odds, first I calculated from pre-test probability, I calculated pre-test odds. From pre-test odds, I calculated post-test odds by multiplying it with the likelihood ratio. So my post-test odds is 3.85. Okay. Now from post-test odds, I have to calculate post-test probability. Okay. So remember, for probability, what you have to do, probability is odds by 1 plus odds. Because in probability, you will take the total population you will take in the denominator, right? So here, probability is odds by 1 plus odds. Here your odds is 3.85. So post-test probability become post-test odds divide by 1 plus post-test odds. That is equal to 3.85 by 1 plus 3.85, which is 3.85 by 4.85, which is 0.73 or 79.3%. So what information we got from so much of calculation is that if based on your clinical signs, you predicted that the possibility of sepsis in the baby is 30%, and now you have sent the blood test and your CRP is positive, and you know the likelihood ratio of positive CRP is 9, then now your confidence of the baby, predicting the sepsis in baby is now 80%. So now you're 80% sure that this baby is having sepsis based on a positive CRP. So that is how you're going to interpret the test. Okay. And this we've already discussed. If it is more than 10, less than 0.1 likelihood ratio, then your confidence is very high. Okay. Last one. I don't know whether I should take this or we can stop here. Pratima, should we stop or because there are, I think, two more slides. Or we can stop here. Yeah, Pratima, you're there?
Yes, sir. Yes, sir.
Okay. क्या करना है? We can stop because it's 9:10.
Yes, yes, sir. I
Okay,
think.
sir.
Hmm.
Kushal is saying, sir, please continue. Sir, please continue. Sir, please continue. Continue, continue, continue. Okay,
Sir,
continue.
कितना अभी sir? How much, Anup sir?
Three more slides. Three more slides means.
हाँ तो फिर कंप्लीट कर लेते हैं ना सर. लास्ट टाइम भी एक we extended for half an hour also on the students.
Okay, fine. ठीक है, ठीक है. So next is a very important concept which I want to give to you is errors in statistics. So there are what you're going to hear is about type 1 error, type 2 error. Okay, all these errors you're going to hear, and what is the actual meaning of these errors that you need to understand. Okay, so here's a question for you. Probability of obtaining a significant result by chance is called what? Is it a type 1 error? It is a type 2 error? It is a beta error or a sampling error? This question you can answer. Kushal is saying A, okay, uh, which is type 1. Chaiti is saying a type 1 error. Okay, any more responses? So type 1, type 1. Great. I think most of you know the answer. So probability of obtaining a significant result by chance. Okay, that means you are studying, for example, an intervention in two groups, A and B. And the truth is that there is no difference in the outcome in the two groups by the intervention. But because of some error, what you found that uh, the intervention is better in group A compared to group B. So you are obtaining a falsely positive result by chance. So that is a type 1 error, also called as alpha error. Okay. Type 2 and beta error are same things. Okay. So basically, when you do a study, there are two groups we are going to compare, or two drugs you are going to compare, for example, A and B. And because of some logical explanation or biological plausibility, you do a study with the presumption that drug A might be better than B. And you want to see in the study mode whether in reality drug A is better than drug B. So your alternate hypothesis here is that drug A is better than drug B. But when you begin a study, you have to have a null hypothesis, and your null hypothesis is that there is no difference between the two drugs A and B, in terms of outcome in a group of population. So drug A and B are similar, there's no difference. Okay, that is your null hypothesis. Now, what happens in reality, in truth, there is no difference within the two groups. So the drug has no effect in A and B, there's no difference in the outcomes in the two groups. So in reality, there is no difference, which means the null hypothesis is true. But because of some error, what you have found out that drug A is better than drug B. That means you are rejecting the null hypothesis when it is true. This is the type 1 error. Or you are getting a significant result by chance. You're getting drug A is better than drug B. You're getting a significant result by chance. This is a type 1 error. So type 1 error in statistics is a serious error. So it's just like we typically give examples that a person is not guilty, but he is being hanged by the court because of some error in the judgment. Okay, so that's a serious error. So that should not happen. That is called type 1 error. Okay, so these are examples typically, and this is what I've just told you. The probability of committing type 1 error is called alpha error. It is the probability of obtaining a significant result by chance, which is false positive. Also, we can express it by rejecting a null hypothesis when it is actually true. So there's no difference, but you're rejecting the null hypothesis. And when we say alpha is 0.5, that means the investigator has set a 5% probability that a significant difference can occur by chance. So this is the basis of p-value. So therefore, we set the p-value of 0.5. So when the p-value is less than 5% for a particular outcome, that means there is less than 5% chance that your difference in the outcome in the two groups has happened because of a chance factor. So therefore, we want to keep it low. And this also forms the basis of your 95% CI or p-value of less than 0.05. Okay. This is type 1 error. And the probability of type 1 error is also called p-value. Okay. Same like in cricket, you're giving a batsman out who is actually not out. Type 2 error is what? There is a difference in the two groups, but you are not able to detect it. So basically, what is happening here, your null hypothesis or null hypothesis is not true. The truth is the null hypothesis is not true, but you are accepting a null hypothesis when it is not true. That means the two groups have a difference. There's a difference in the two groups, but you're not able to pick it up. Okay. So probability of not finding a difference when it is actually true or actually exists is false negative. This is called type 2 error. So here you are accepting a null hypothesis when it is not true. This is the other way to express it. And this is also the probability of committing a type 2 error is called beta. And this is used to calculate power. So power is 1 minus beta. Okay. So how much you want to keep your type 2 error acceptable? So 10% to 20% is acceptable in studies. So therefore, most studies will have a power of 80% of or 90%. So these two, type 1 and type 2 error, are used in your sample size calculation. So simply speaking, look at this 2 by 2 table. So the truth is that the intervention is not better than control. That means there is no difference, but your study finds that the intervention is better than control. This is a serious error. This is type 1 error or alpha error. The truth is the intervention is better than control, but your study is not able to pick it. And this is your type 2 error or beta error. That's it. Okay. So Gujan, you can go to the next question.
So a researcher wants to test probiotics to reduce NEC in VLBW infants. Baseline NEC incidence was 10%. Expected incidence after probiotic, what we were expecting was 5%. You plan to conduct the study with significance level alpha, that is type 1 error of 0.05 and a power of 80%. And there was equal allocation to the two groups. So questions are, name the 4 key parameters required for sample size calculation and what happens to sample size when power increases from 80% to 90%. So the parameters required for sample size calculation that you have to type in the chat box first. Please be quick. What is D here? So there are like 4 key parameters. So first one is effect size. Effect size is difference between the expected event rate and the baseline event rate. In this question, particular question, what was the baseline? That was 10%, and we were expecting it to reduce to 5%. So effect size will be D is equal to 10 minus 5, that is 5%. Alpha, the second parameter needed for sample size calculation is alpha error. The third one is power. So both of them have been beautifully explained by Dr. Anup. And last is baseline event rate or variability. Baseline event rate in this particular question is 10%. So the 4 key parameters are type 1 error, power or 1 minus beta, baseline event rate, and effect size. So what happens to the sample size if the power increases from 80% to 90%? So next slide. So as we know, the formula for sample size calculation will for two proportions will be n is equal to n is a sample size is equal to 2 times the Z alpha. Z alpha represents your level of significance or type 1 error plus Z1 minus beta, that would be your power, into small p. Small p is your average of proportions. That is P1 plus P2 by 2, and where P1 is your in the event rate in the one group, that was 10%, and P2 will be the event rate in the expected event rate in the next group, that is 5% here. So P is equal to P1 plus P2 by 2, and Q is your Q1 minus P, and D is effect size that I have already discussed, that the difference between expected and baseline event. So here we can see that sample size is directly proportional to the power. So if the power increases, your sample size will also increase. And on the right side, we have this table where we have Z values for conventional values of alpha and beta. And we can take an example. So should we take this example for sample size calculation? Next slide. So a study is planned to check the effectiveness of drug A in preventing BPD. Okay. From previous studies, the incidence was found to be 60% for the BPD. So this will be your P1 will be 60%. Reduction in the incidence of BPD to 20%, that is P2. This was the expected outcome, 20% incidence of BPD, that is P2 is 20%, will be considered significant for the effectiveness of the drug. What should be the sample size with a type 1 error of 5% and power of 95%? So again, coming to the calculation part, n is equal to 2 times of Z1 minus alpha, sorry, Z alpha. Z alpha for 0.04, here we can see this is 1.96, and Z1 minus beta for a power of 95%, that is beta of 0.05 is 1.64. So 1.96 plus 1.64 ka whole square into small p was P1 plus P2 by 2. P1 was 60%, P2 was 20%. So 60 plus 20, 80 divided by 2, that would be 40. Then coming to Q, Q was 1 minus P. So 100 minus 40, that comes out to be 60. And divided by D, that was effect size, P1 minus P2, that is 60 minus 20, that will be 40. And this is somewhere 40. So 40 babies will be should be included in each group, so that we can effectively tell you the outcome that yes, we are able to detect the difference or not. Less than, if we are including less than 40 babies as a sample, we are not able to enroll 40 babies in each group, then we are not basically entitled to effectively tell you the outcome. So this was about sample size calculation.
Okay. So last question. Okay, last question, and I think we all need to go have our dinner. So the last question is on using the correct statistical test, and let me see how many of you can attempt this. 25 preterm infants are on mechanical ventilation, and they receive varying dose of hydrocortisone for 9 days, and the aim is to achieve extubation. And the baseline blood pressure is measured before hydrocortisone and after hydrocortisone. And similarly, you have baseline blood pressure measured in 50 matched infants who did not receive the intervention. Okay. And there's a definition of hypertension as systolic blood pressure more than 98th percentile. And here we are assuming that the blood pressure and the hydrocortisone dose are normally distributed. Now you have to choose the statistical test which you're going to apply. So let's suppose you have done a study and you want to choose the statistical test. Okay. So you want to compare, so what was in the two groups, hydrocortisone treated and not treated. You want to compare the proportion of patients who are hypertensive versus non-hypertensive. So what test you're going to apply for number A? And should I wait? Okay, someone is saying pair t-test, pair t-test, pair t-test. Okay. Number 2, compare change in mean blood pressure from baseline and compare hydrocortisone versus no hydrocortisone. And third is compare cumulative dose of hydrocortisone to change in systolic blood pressure from baseline, two continuous variables. So A, B, C, there are 3 sections, and A, both categorical because presence or absence. So chi-square, someone is saying chi-square, then pair t-test. Okay. Any other responses? This is your last question, guys. Okay. So let's come to the first question. So here you're right. We are comparing the groups hydrocortisone treated and not treated. This is one group. And we are looking at hypertension or absent or present. So these are two categorical variables. Okay, here we have categorical variables where the question is yes, no. And we are comparing two categorical variables in two groups. So whenever you compare categorical variables, whenever you're comparing proportions, so proportion of hypertension in group A versus proportion of hypertension in group B, so then you will be applying a chi-square test. Okay, you will be applying a chi-square test. You will not be applying any pair test. It's a chi-square test because it's a categorical variable. And if the value in any column is say less than 5, in that case, you will apply a variant of chi-square test, which is the Fisher exact test. That's the answer to the first question. Second is you're comparing the change in mean blood pressure. Okay, you are comparing the change in mean blood pressure. Where are you comparing? In the two groups, hydrocortisone versus no hydrocortisone. So in two groups, when you're comparing mean, then you will apply the student t-test. So mean in two groups and the data is normally distributed, you will apply student t-test. When the data is not normally distributed, then you might be comparing median, then you will apply Mann-Whitney test. Okay, remember this is a continuous data. This is a continuous data. Two groups, student t-test or Mann-Whitney test. Three groups, then you will do ANOVA. If you want to compare means in three groups, then you will do ANOVA test if the data is normally distributed. Okay, so just comparison of mean in two groups, simple student t-test. Pair t-test we use in the same group if we want to see what happened before and after intervention. Okay, so the group has to be same group before and after intervention. Then you are having a paired measurement in the same group, then you will use paired t-test. But if there are two groups, when you are comparing means in two groups, then you use the student t-test. So that difference should always be there, right? Next is you compare the cumulative dose of hydrocortisone for change in systolic blood pressure. So two continuous variable, you're looking at the relationship between two continuous variable. To look at that, you have to do correlation. So if data is normally distributed, you will use Pearson correlation. If non-normal data, then you will use the Spearman correlation. Okay. Now, if you want to look into the relationship between the two groups and predict one group based on other, then you will go into linear regression if the data is again normally distributed. Okay. So grossly speaking, this is how you're supposed, this is the chart which we show to most of our students. So average of two groups, you're looking into two groups and you're just comparing the averages, the means. You can do a independent t-test or student t-test if the data is normally distributed. For non-normal distribution, you will compare median. You can use the Mann-Whitney test. When there are three groups, you are going to compare means in three groups. So here your data is scalar. In that case, average in the three groups or more, you do by ANOVA or one-way ANOVA test. And the non-parametric test for the same is KW test or the Kruskal value test. If you're doing in the same group, you're looking at paired observations, before and after kind of observation. Okay. Then you do a pair t-test. Okay. Or you can do the WSRT test or Wilkinson signed rank test. So same group before and after kind of intervention. In the same group, if you have three or more repeated measurements, then the parametric test is repeated measure ANOVA, and the analog for the non-parametric test is Friedman test. Okay, so this is what you're supposed to remember in your exams. And then if you want to look at relationship of two continuous variables and you presume they follow a normal distribution, so both are in the scalar, so both are in continuous, then you can look at the relation by doing a Pearson correlation if it is normally distributed. and Spearman. If it is non-normal, then you have to order them out. If you want to predict one value on other, and if you have a scalar relation, then you do a simple linear regression. You can do that if it is normally distributed. And in case if you have the outcomes, they are nominal, they are binary. For example, want to look into mortality, you want to look into NEC, those kind of relationship you want to look into, then you have to apply logistic regression. And when you have categorical variables in two groups, then you do the chi-square series. So this is the very briefly I've just told you what are the various tests you apply in various conditions. So that's it from our side. This is last question. Gunjan, you can finish this quickly and then we'll leave. Gunjan, you're there?
So a meta-analysis was conducted to compare 4 probiotic preparations, A, B, C, D, for prevention of NEC in very low birth weight infants along with placebo. So what is this type of statistical analysis which has been represented by this diagram? First question. You can quickly type your answer in the chat box. Good. Network meta-analysis. Okay. What does each circle or node represent? And what does the line connecting the two nodes indicate? If the line is connecting the two nodes, what does it indicate? Okay. And next slide, sir. Which treatment appears to have the largest number of participants just by looking this diagram? What does the thick line between B and C represent? And can treatment A be compared with B even if no direct trial exists? We can see there is no line connecting A and B, but still can it be compared or not? So yes, the answer is network meta-analysis, and it compares multiple interventions simultaneously with using both direct and indirect evidence. And each node or circle is representing the treatment or intervention group. In this case, they are A, B, C, D, as well as placebo. And what does the line between them indicate? That yes, randomized trials comparing both the studies exists. And which treatment appears to have the largest number of participants? Whichever node is the largest, that in this case, this is the C. So treatment C appears to have largest number of participants. And thicker line between B and C. We can see there is thick line between B and C. So, so more direct comparative studies have been done between B and C. And last, yes, A and B can be compared with the help of common comparator like C. A has been compared with C. B has also been compared with C. So using this comparator, we can compare even A and B, although there were no direct trials to compare these two interventions, A and B. And even with placebo, can be used as a common comparator. So this was network meta-analysis. And briefly, everything about network meta-analysis. It was a brief introduction.
Okay, so very exhaustive lecture, I think, class, lot of questions, lot of difficult ones. And we also wanted to cover agreement, Karpaz Cohen, blind elephant plot, survival analysis, Cox regression, hazard ratio, Kaplan-Meier, correlation, regressions, but we don't have enough time to teach you everything in one day. I really thank Gunjan for being so supportive and preparing this question, my dear co-faculty, and thanks to Pratima and Swati again for conducting this course, and Sushant, and thanks to all the participants. If you have any question you are interested to ask, you can unmute yourself and ask. Otherwise, we close the session. It's 9:30.
Thank you so much, sir. Participants, anybody wants to talk or unmute and say something? Sir is also expert in another study design, another type of design, which is quality improvement, sir. I think uska bhi thoda bahut we can add some assessment at the end of the session.
Kushal is
So
saying,
do
take
read
another
up,
class.
yeah, do read up run charts and the rules of run chart, which is another design, and also the guidelines for reporting any study or something like that. So that is also one of the part of statistics. So you can read up the equator guidelines also. So Thank you, sir. I think if there are no questions, anyone you want to ask something in the chat or unmute and ask?
We are asking for one more class for all these difficult topics. I think they are not bored today after 2.5 hours. We are bored already taking the lecture.
Actually, sir, mathematics and statistics, I think it does
So
take a lot
many.
of attention, no? So,
Yeah.
yes.
So hats off to the participants. I mean, this Prakash
Mm,
and so many people
exactly.
who can still hanging on.
But it was a very comprehensive, elaborate, and very in-depth interpretation and framing of questions. It was not simply just one-word answer or something. You just uh, framed the questions through examples and real study designs and all. Thank you so much, Gunjan and Anup sir. Thank you so much. It was a learning for me also, and a very essential part for a clinician, not only a researcher, but for also clinicians, because we need to interpret the evidence which is coming and we need to know the basics. So thank you. Thank you so much.
Okay. Thank you, everyone.
Thank you,
Thank
Thank
you.
ma'am.
you,
Good
sir.
night.
Thank you. Good night, sir.
Good night. Thank you, Gunjan. Good night. God bless
Thank
everyone.
you,
Bye bye.
sir. Thank you, ma'am.